Today, let's discuss about Norton's theorem. So what is Norton's theorem? So it says that a linear circuit can be represented by a single current source in parallel with the corresponding equivalent resistance of the linear circuit. So if you have this linear circuit, you have your points A and B. Okay. The short circuit current we measure by shorting points A and B is called the Norton current. Okay. I sub N, Norton current. Okay. The equivalent resistance of the linear circuit is called the Norton resistance, this one. Okay. So this linear circuit can be also represented by having a current source in parallel with the equivalent resistance R sub N. So here are the terms, okay? So at the right side, at the other side of points A and B, the right, we have the load resistance R sub L. Okay? So Thevenin's theorem says that you have your linear circuit can be expressed in terms of a single voltage source in series with the equivalent resistance. So this time for Norton, you have your current source in parallel with the equivalent resistance. So Norton's theorem is a derivation actually from Thevenin's theorem. Okay. Okay, let's go straight to the example. Solve for the Norton current and the Norton resistance at points A and B, given this circuit. Okay, so we need to know the Norton current, Norton resistance. Oop, Naruto. Okay, Naruto. Okay, in Norton, always remember that the circuit equivalent is a current source in parallel with the equivalent resistance. So again, Norton, current source, parallel resistance. Norton, current source, parallel resistance. Okay, Naruto, let's move on to our mission. Our mission is to solve for the Norton resistance and Norton current. Let's solve for the R sub N first. Okay, we have the circuit, right? In solving for the resistance, we need to turn off all the independent sources. Yep, turning it off. So we have 2 amperes open, our voltage source shorted, okay? Then measure the resistance at points A and B. So if you are going to tap your DMM, okay? DMM here, points A and B, what is the resistance? So the equivalent circuit right now is we have 8 ohms in series with 4 ohms in series with 8 ohms, right? Because this is open. So it's as if that this does not exist. So we only have this in series. So 8 plus 4 plus 8 is 20 ohms. And then the equivalent resistance here is in parallel with 5 ohms. So 20 times 5 over 20 plus 5 equal to 4 ohms. So that is our equivalent resistance at points A and B. R sub N is equal to 4 ohms. Or our Norton resistance is 4 ohms. Okay? Next, let's proceed with our second mission to get the Norton current. So, Norton current, we need to turn on all independent sources since we turned it off previously. And also, we need to short out points A and B, okay? And that is our Norton current. Okay, previously in Thevenin voltage, what we do is we get the open circuit voltage at points A and B, but in Norton current, we need to short the points A and B, okay? Or the, whatever the designated labeling. So, I chose mesh analysis in analyzing the circuit, okay? We have this first mesh and the second mesh, okay? You might be curious why there are only two meshes. There are two loops only. Okay, so why? This part, it's not hard to understand. So this one is a mesh, okay? But this one, why does it flows only here? It did not flow here at 5 ohms, only at uh, this loop. Yeah. So, okay, the current, the tendency of the current is to flow the least resistive path. So this wire has 0 ohms, right? 0 ohms, 0 ohm. Okay, it doesn't have any resistance, so current will flow freely here, right? So if you're going to choose, the current will choose, oh, I will flow here and flow here. Which way will I go? Of course, you will flow uh, at the branch in which there is no resistance. Okay, so all of the current will flow at this side, not at 5 ohms, this path. Okay, so no current will flow in 5 ohms. All of it will directly flow here. So yeah, this one is a high resistive path. This one has no resistance path. So since this is least resistive, then current flow here. Okay, it will not flow here in 5 ohms. Yep. Okay, let's go on. Do we mesh analysis? Okay, the steps we need to solve for the mesh currents next is solve for the short circuit current. Actually, I sub 2 or the second current mesh 2 is already equivalent to the Norton current because the current that flows here, I2, is it's the same, right? The current that flows in this branch, this wire. Okay, so let's move on. So at mesh 1, you see this is under case 1. Okay, we have a 2 ampere current source, an independent 2 ampere current source. Okay, so I1 is equal to 2 amperes automatically. Same direction, so it's positive. Next, let's move on to the second mesh. We have 12 volts, then negative 4 I1. Okay, the contradicting current is negative I1. Okay, multiplied by 4, then plus 4 plus 8 plus 0 plus 8 times I2. Remember, we did not go here in 5 ohms. We did not flow through 5 ohms. So 4, 8, and 8. 4, 8, 8 times I2. Okay, next, 12 is equal to negative 4I1 plus 20 I2. Okay, so 12 plus 4 times 2 equal to 20 I2. So that is equal to 20 equal to 20 I2. Then I2 is equal to 1 ampere. Okay, and okay, since I2 is equivalent to our I sub n and the short circuit current, so it's also 1 ampere. Yeah. So the Norton current is 1 ampere. Okay. Lastly, excited. Lastly, since this is the last slide. Okay, so this one, this circuit 3, okay, can be expressed in a single current source with a single current source in parallel with the equivalent resistance R sub n. Okay, we have I sub n equal to 1 ampere, then R sub n equal to 4 ohms. So I sub n 1 ampere, R sub n 4 ohms. Okay, that's it.